Good morning. So this is 11th Astronomy Department of ECG, SRM Institute of Ratanpur. So in this video lecture, we are going to discuss about multi-carrier modulation technique, introduction to OFDM, then multi-carrier modulation. In multi-carrier modulation, we are going to discuss about cyclic input channel model as well as how we are going to calculate SNR value. So in previous video lecture, we have discussed about introduction as well as basic. So evaluation of mobile communication system. Then we discussed about evaluation of cellular technology. Then we discussed about 3GPP, third generation project partnership. Then last we have discussed about WiMAX system. First, in this today video lecture, we are multiplex. What is multiplex? So by the name itself, you can tell the answer. Multi-input, it will be converted as a single output. That is nothing but multiplexing. Multiple n number of an input and then it will give single output. Capacity of transmission medium usually exceeds capacity required for transmission of a signal. So once if you are going to communicate, the capacity transmission medium plays a major role. How it's going to play major role means the capacity of transmission medium usually exceeds the capacity required for transmitting the signal from one place to another place or source to destination or sender to receiver. So in order to fulfill the capacity of transmission medium usually exceed the capacity required for transmission of a signal by the help of an multiplexing. It will carry multiple signals in a single medium. That is nothing but the n number of an input. It will be communicated with a single medium access technique. That is nothing but multiplexing. So according to that multiplexing, here we are going for FDMA, TDMA, CDMA, WDMA. That is nothing but time division, code division, wave division as well as frequency division. So these are the various multiple medium access technique we are going to be used in communication field. So first multiplexing is nothing but carrying a multiple signal on a single medium. By using this, what are the things you are going to be benefited? More efficient use of transmission medium. Why? Because means it's going to carry the multi-signal. So multi-signal means you can think, for example, here we are going to transmit 10 signals means for each and every signal, here we are not going to give an single medium access. These are all 10 input. It will be clubbed together and then it will communicated via only single medium access technique. So it is going to be more efficient use of transmission medium. For wireless, what is meant by transmission medium? So we have clearly said multiplexing is going to be carrying that multiple signal in a single medium. With this we can use our transmission medium more efficiently. How you are going to use efficiency with the help of a transmission medium? So you should know what is meant by transmission medium. Then only we can able to understand how efficiently it has been useful. First we will discuss about the concept of multiplex. So as I said, you can able to see this n input in transmitter side, it will be combined into one single link. And then here we are going to communicate with a single medium access, that is nothing but channel. As in an output side, this single input, once again it will be given to multiple output. So that was the fundamental concept here. So n input is going to be combined as a single link in your transmission side. The same in if you are seeing receiver side, this single input, it will be given to n number of an output. So this was the fundamental concept we are going to be used for multiplex. N input to n output with the help of an single link with n channel. So multiplexing technique, as I said, here we are going for various multiple filtering. The first one is nothing but frequency division multiplexing. So frequency division multiplexing means here for each and every user, they are going to give an specific frequency range. So they will be communicating to the receiver side with their own frequency. The frequency range will not be changed. So that is nothing but frequency division multiplexing. For best example of a frequency division multiplexing, you are going to drive the car. In the car, you will be having that radio service. In your radio service, if you want to hear any specific radio broadcasting channel 1.1 or 98.3 or 95.4. So according to that frequency, you are supposed to tune your channel frequency range 98.3. Then only you can able to hear clearly what the broadcasting is going currently. If you are going beyond or if you are going below, what will be the thing means noise plays a major role. You cannot able to hear the broadcasting clearly. Why? Because means your frequency range either it will be beyond or either it will be below. So you should tune your frequency 98.3. Then you can able to hear the broadcasting clearly without any noise interpretation. So that is nothing but frequency division multiplexing. Takes advantage of the fact that the useful bandwidth of medium exceeds the required bandwidth of a given signal. So this was the frequency division multiplexing. This clearly I have been given one common example. Next, time division multiplexing, TDM, takes advantage of the fact that the achievable bit rate of the medium exceeds the required data rate of a digital signal. So time division multiple means for each and every subscriber, there will be a specified time slot. So they will be communicating their channel or medium access according to their time slot. Then there won't be any pollution. Pollution means it will not mix or it will not go for any interference with the present user as well as the next user. So that is nothing but time division multiple access technique. Here we are going for TDM, so time division multiplexing. So each and every user, there will be they will be given to a specific time slot. According to the time slot, they will interrupt that medium or channel. So in order to avoid the pollution. So that is nothing but time division multiplexing. So you can see the difference between FDM and TDM in diagrammatic exponent. So first that blue color is nothing but frequency division multiplexing. That red color is nothing but time division multiplexing. In blue color you can able to see x-axis as well as sorry here. In y-axis here we are going for time. X-axis we are going for frequency. The same will be carried out for time division multiplexing. So x-axis we are going for frequency, y-axis we are going for time. The only one difference what we have specified for each and every user, it will be a given frequency range. They will be communicating to the user receiver. Time division, there will be a given time slot. They will interrupt the medium or channel. So in x-axis, clearly you can able to see in FDMA channel 1, channel 2, channel 3, channel 4, channel 5, channel 6. So how many channels here we are going with? 6 channels. In y-axis, we are going for time duration. For each and every channel, how much the user have been taken. So in that way, we can able to calculate FDMA. The same if we are going for TDMA, that is the time division multiplexing. Here is there by that name FDM. Frequency plays a major role. So in each and every frequency, F1 channel 1, F2 channel 2, F3 channel 3, F4 channel 4, F5 channel 5, F6 channel 6. So total number of channel 6. Total number of frequency 6. So it has been named as a frequency division multiplexing. Now we are going to discuss about time division multiplex. So here in frequency we are not going to consider. Why? Because means we are looking at time division multiplex. So for each and every time slot, here we are going for channel 1, channel 2, channel 3, channel 4, channel 5. In that way it will be going for T1 channel 1, for T2 channel, for T3 channel 3. Why? Because it is an time division multiplex. For each and every time slot, each and every user, they will use the channel. So that was the difference between FDM as well as EDM. So previously we have discussed about that description. Here we have discussed about diagrammatic manner. Next, OFDM, orthogonal frequency division multiplex. So this OFDM, it has been come under third generation OFDM slash OFDMA, orthogonal frequency division multiplexing or orthogonal frequency division multiple access, OFDM or OFDMA. These plays a major role in your cell phone or in your mobile communication. So how OFDM create great expansion in wireless network? How means greater efficiency in each and every bit per second or hertz. This bit per second is nothing but time, hertz is nothing but frequency. So it created great expansion in wireless network. How means greater efficiency in bit per second as well as hertz. Main air interface in the change from third generation to fourth generation. Mainly it has been implemented in between third to fourth. That is, we are going to move from third generation to fourth generation. That is nothing but fourth generation. We are going to use smartphone. Smartphone means we are going to use only for mobile communication. That is mobile data. Voice call will be minimum. So we are going for maximum data rate. If you want to get that maximum data rate means the only modulation technique OFDM or OFDMA. Also expand 802.11 rate. Third, critically the technology for broadband wireless access. That is nothing but WiMAX. Next. How the OFDM is going to be work? It is also called as a multi-carrier modulation. Multi-carrier modulation means carrier 1, carrier 2, carrier 3. That is nothing but user 1, user 2, user 3. So if we are going for more user means that is nothing but multi. If you are going for more carrier, that is nothing but multi-carrier. So that only it is also called multi-carrier modulation. Next, start with a data stream of R bits per second. As I said very clearly, why we are going to use OFDM in because we are supposed to go for maximum data rate. Then only your smartphone can able to cope up. Without data rate, we cannot able to go for any internet. So once if you are once if you are going to have sufficient data rate, then your mobile equipment, once this two is going to be fulfilled, then you can able to enjoy your internet service. So in this aspect, the first point what we are going to be considered means it's going to start with a data stream of R bits per second. Could be sent with the bandwidth of NFB. The duration is going to be 1 by R. Why? Because means R is nothing but data. Right. Here you are going to send with bandwidth NFB. F is nothing but your frequency of bandwidth. N is nothing but N number. So obviously your duration of bit will be 1 divided by R. This OFDM split into n parallel data streams. As I said, it is going to be named as a multi-carrier modulation. So your carrier frequency, it will be divided into subcarrier. So that only it is going to be called as a subcarrier. Each with bandwidth FB. FB is nothing but frequency bandwidth. The data rate is going to be R divided by N. R is nothing but your data, N is nothing but N number. OFDM split into N parallel data streams. It is also called as subcarrier modulation technique. Each with bandwidth and data rate is going to be R divided by N. In this manner, OFDM works. Next, O stands for orthogonal. So you are supposed to know what is meant by orthogonality. So O orthogonal, F frequency, D division, M multiplexing. So FDM already we have discussed, frequency division multiplexing. So now you want to know about the orthogonal. Then only you can able to know what is meant by OFDM. The spacing of the FB, that is frequency bandwidth, allows tight packing of signal. Actually, with overlapping between the signal at the spacing of FB, 2 FB, 3 FB, 4 FB, it will be keep on going. The spacing of frequency, it is denoted by FB. It's going to allow tight packing of signal. Right? Actually, with overlapping between the signal. The signal spacing is going to be FB, 2 FB, 3 FB, 4 FB. Like that, it will be keep on. So what the first point is going to be specified is, even though you are going for n number of signal which is going to be tightly packing, it will go with overlapping between the signal, but it will not mix up between one to another. How means it will maintain the orthogonality between one signal to another signal. With that orthogonality, if you are going to tightly pack multiple signal, it will not mix up with the nearby signal. The choice of FB is related to the bit rate to make the signal orthogonal. So as I said, orthogonal plays a major role between one signal to another signal. Now second point, the choice of frequency bandwidth is related to the bit rate in order to make the signal orthogonal. Once if you make the signal orthogonal, then only it is going to be an OFDM, orthogonal frequency. The average over bit time for S1 as well as S2, it is going to be 0. Receiver is able to extract only the S1 of the signal if there is no corruption in the frequency spacing. Then only easily we can able to retrieve by the receiver. Why? Because means in transmitter side we are going to tightly pack the signal and we are going to maintain orthogonality, then we are going to transmit. The receiver, they want to extract that original signal. The condition, it should not go for any corruption in frequency spacing, FB, 2 FB, 3 FB. Right, that was the second point. The traditional frequency division multiplexing makes signal completely frequency overlap. Right. OFDM allows overlap with greatly increasing their capacity. How increasing their capacity means by maintaining the orthogonality between one signal to another signal. That is nothing but orthogonality. So this was the diagrammatic explanation. So first one, that is subdivision A, subdivision B, sub C. Subdivision A, 3 subcarrier in time division or time domain. So green color red color, and then dotted black color. So these are all the three uh, carrier frequency we are going to be have, that is three subcarrier in time domain. So our time domain means here we are going to paste the signal FP, 2FP, 3FP. So how you are going to represent means 1 divided by FP, that is T is equal to 1 divided by FP, T is equal to 1 divided by 2FP, T is equal to 1 divided by 3FP. So in this way we are going to represent three subcarrier in time domain. Next we are going to discuss subdivision B. Previously we have discussed three subcarrier in time domain. Next we are going to discuss the same three subcarrier in frequency domain. In frequency, how you are going to represent these three subcarriers with the help of orthogonal. So you can able to see the clear cut picture. Red color will have the proper sinusoidal signal, dotted black also having the sinusoidal signal, green also having the sinusoidal signal. From red to dotted black and then dotted black to green, they are going to maintain the orthogonal uniformly. Now I hope you understand. So in previously you cannot able to see the orthogonal where in time domain, but in subdivision B we can clearly see we are going to maintain the orthogonal from red signal, dotted black signal as well as green signal. Then only it is going to be named as an orthogonal frequency division multiplex. Next, coming to the third subdivision, that is nothing but part C. Three carrier using traditional FDM. Traditional FDM means here they are going to split these red color, dotted black as well as green one based on that traditional. So this was the illustration of orthogonality of OFDM. Concept of orthogonality or orthogonality concept. In an given OFDM subcarrier bit time of T, FB is nothing but frequency of bandwidth must be multiple of 1 divided by T. F is equal to 1 divided by T. Recall FB is frequency of one FDM subcarrier, only one OFDM subcarrier. Example, IEEE 802.11n is going to be a wireless local area network which is going to be have 20 megahertz total bandwidth. Only 15 megahertz can be used. The total subcarrier is going to be 48. So obviously the FB equals to n divided by subcarrier. N is nothing but 15 divided by subcarrier 48. So you will be getting 0.3125 megahertz. This signal is translated to 2.4 gigahertz or it will be 5 gigahertz bandwidth. In this way they will be calculating FB. FB is equal to n divided by B. N 15 and B 48. Now we are going to discuss about the advantages of OFDM. So frequency selective fading only affect some subcarrier, can easily handle with a forward error correction coding. So easily you can able to take care this situation with the help of a forward error controlling code. Most importantly, OFDM overcomes ISI, that is nothing but inter-symbol interference. ISI is a caused by multi-path signaling arriving in later bit, multi-path propagation. The signal will be arrived to the receiver in different time slots. That is nothing but multi-path propagation. So ISI is a caused by multi-path signal arriving in later bit. OFDM bit time are much, or in sometimes much longer. Why? Because means this ISI is dramatically reduced. So designed a side n is chosen, so the RM value, that is root mean square delay spread, is significantly smaller than the OFDM bit time. So this was the designed one. It not be necessary to deploy equalizer to overcome ISI. Eliminates the use of this complex and expensive design. So why we are going to use this in order to overcome the complex as well as expensive design. So these are the advantages, or these are the benefits of OFDM. Now we are going to implement this OFDM system. So IFFT, inverse fast Fourier transform, frequency domain to time domain. So OFDM concept could use n oscillators for n different subcarriers. So expensive for transmitter as well as receiver. It will be carried out in transmitter side. IFFT will be carried out in transmitter side. IFT is nothing but algorithm. Inverse fast Fourier transformation. DFT, discrete Fourier transformation. It will be on receiver side. So DFT process digital signal. If n is a power of 2, the computational speed dramatically improves by using this fast version of discrete Fourier transform. Transmitter takes a symbol from each subcarrier, makes OFDM symbol, uses inverse fast Fourier transform in order to compute the data streams to be transmitted. Then OFDM symbol provides the weightage of each subcarrier. Then it is sent on carrier using only one oscillator. So from the transmitter side, it's going to take the symbol from each subcarrier in order to make OFDM symbol. After making that OFDM symbol with the help of an IFFT algorithm, here we are going to computate, or here we are going to compute the data stream what we are going to be transmitted. Then that OFDM symbol provides weightage for each subcarrier. Then it's going to be transmitted on carrier by using one oscillator. So this was the block diagram of OFDM. So input here we are going to be given in the format of bit stream. After we are going to give your input bit stream, the first process is going to be serial to parallel conversion. So what are the bit stream you are going to given, that will be converted serial to parallel. After that, here we are going to use an algorithm, inverse fast Fourier transformation, in order to compute your signal. After using this IFFT algorithm, once again we are going to convert parallel to serial. Then we are going to add the cyclic prefix. Then we are going to use ADC, that is analog to digital converter. Then we are going to transmit. So these are all the operations is going to be happen in transmitter side. The same in receiver side. It will receive, it will convert into DAC, that is digital to analog converter. Then in transmitter we have add the cyclic prefix. First thing, it will remove the cyclic prefix. After removing, it will convert serial to parallel conversion. Then a receiver we are going to use FFT algorithm, that is nothing but fast Fourier transformation. After that, it will convert parallel to serial. Then it will be your output. So this was the complete OFDM block diagram. Serial to parallel, IFFT algorithm, parallel to serial, adding cyclic prefix, then ADC transmission, receiver side, DAC, digital to analog, removing the cyclic prefix, serial to parallel, FFT algorithm, then parallel to serial, then right. Next, what is meant by cyclic prefix? So in transmit side, you are going to add cyclic prefix. In receiver side, you are going to remove the cyclic prefix. OFDM long bit time eliminates most of the ISI inter-symbol interference. OFDM eliminates inter-symbol interference. OFDM also use a cyclic prefix which is going to be denoted by CP in order to overcome the residual ISI. Add additional time to OFDM symbol before the real data which is going to be sent. Either it is going to be called by God interval, or here we are going to diminish ISI before the data which is going to start. So for this purpose, we are going to add the cyclic prefix in transmitter side. It's going to add additional time of an OFDM signal before what we are going to send the real data with the help of God time or God band. Also, it will diminish the ISI before the data starts for transfer. Design aside, the data from the end of OFDM symbol is used as the purpose, which is going to simplify the computation. So by using this cyclic prefix, we are going to simplify the computation. Okay. Bit C, serial to parallel, IFFT, parallel to serial, adding cyclic prefix. Then we are going for analog to digital conversion. Then we are going for transmission. That we are going to see what they. Then what are the issues we are going to face with OFDM? First issue is nothing but PAPR, peak to average power ratio. For OFDM signal, this ratio is much higher than for single carrier signal. OFDM signal is a sum of many subcarrier signals. Total can be very high, or in other points it will be very low. So peak to average plays a major role in OFDM signal, which is going to be much higher than the single carrier signal. So OFDM signal is a sum of many subcarriers. At a point, it will be very high or it will be very low. The power amplifier needs to amplify all the amplitude. Why? Because it peaks to average power ratio. Certain point it will go for peak value. So how it's going to be, where we are going to face the difficulty is, here we are supposed to amplify all the amplitude equally. V out is equal to K into V in. So K is some constant, V in, V out, you know. Next solution could reduce the peak amplitude called input backup. By using this input backup concept, here we are going to reduce the peak amplitude. But this could increase the signal to interference pulse noise ratio. That is nothing but SINR, signal interference noise ratio. SNR is nothing but signal to noise ratio. SINR is nothing but signal interference noise ratio. The noise and interference would be relatively stronger. Why? Because your signal is weaker. In your communication, noise is going to be maximum, obviously signal will be lesser. If the signal is going to be higher, your noise will be lesser. That was the concept. Specific PAPR reduction technique can be used. Specialized coding, or you can able to adjust the phase, or you can go for clipping transfer concept, or in other terms, you can able to use SCFCFA, single carrier frequency division multiple access technique. How you are going to reduce means any coding or phase adjustment or clipping or clamping or SCF. ICI, that is inter-carrier interference. So OFDM frequency are spaced very precisely. Channel impairment can corrupt this. Cyclic prefix helps reduce ICU, but CP, that is cyclic prefix time, could be eliminated so as to improve the spectral efficiency. A certain level of ICI may be tolerated to have smaller cyclic prefix. Doppler effect, mismatch oscillator, or even one subcarrier can cause ICI basically. Subcarrier may need to increase, could be different pulse shape, self-interference cancellation, or frequency domain protected. So previously we discussed ISI, inter-simple interference. Now we are going for inter-carrier interference. So by using this inter-carrier interference, what was the thing is going to be happening? OFF frequency are separated very preciously. Then the channel impairment can be corrected. Then third one, cyclic prefix is used in OFF in order to reduce ICI. Then Doppler spread mismatch oscillator or even one subcarrier can cause I. OFEM, orthogonal frequency division multiple access. Uses OFEM to share the wireless channel. Different users can have different slices of time, different group of subcarrier. Subcarrier are allocated into called subchannel or resource for too much computation to allocate every subcarrier separately. So this was OFEM. OFEM is to use OFEM to share the wireless channel. Different user can have different slice of time, that is different time slot and different group of subcarrier. So this is going to be called as a sub-channel. For too much computation to allocate every subcarrier, we are going for separately. Allocation of subcarrier will be separate. The sub-channel allocation adjacent subcarrier similar with the SM, SIR, SINR, symbol interference noise pollution. Must measure to find the best subchannel. Once if you are going to measure, then easily we can able to allocate it. Regular spacing subcarrier and randomly spacing subcarrier. So these two placements, regular spacing subcarrier, diverse SINR. Randomly spacing it will diverse and it will reduce the adjacent cell interference. So this is nothing but OFEM. Now we are going to see with the diagrammatic representation. So first one is nothing but OFEM, frequency of subcarrier. Second one is nothing but OFEM, adjacent subcarrier. Pilot carrier, pilot carrier. The first signal will be pilot carrier in your OFEM technique. So with this we are going to transmit the signal. So each and every subchannel will be having their separate channel allocation, subchannel allocation. So with this we are going to use OFEMA effectively than OFEM. Next, so what are the issues and how the issue is going to be overcome by using OFEM? That with the help of single carrier frequency division multiplication. So SCFPMA has a similar structure and performance what we have discussed in OFEMA. The advantage but lower PAPR. If you are going to use single carrier FPMA, the PAPR will be very low. The same if you are going for OFEM, PAPR will be high. Mobile user benefit their battery life, power efficiency as well as lower cost. Why? Because means if we are going for low power consumption means obviously the battery life will be increasing, power efficiency will be increasing, cost will be lower. Good for uplink. SCFPMA will be used for uplink communication. Uses extra DFT operation and frequency equalization compared to OFDM. So it's going to use DFT operation and frequency equalization by comparing with OFDM. Why? Because what was the disadvantage in OFDM, it will be fulfilled with the help of a single carrier frequency division multiplier. So DFT prior to IFFT, that we know, spread the data signal over all the subcarriers. That was the point. Every data symbol is carried by every subcarrier. So just like that, we cannot use DFT prior to IFFT. That you know very well. The data signal it should be spread or it should be given to all subcarriers. Then every data symbol is carried by every subcarrier. Then multiple access is not possible. At one time, all subcarriers must be dedicated to one user. Multiple access is provided by using different time slots. So that multi-access is not possible. So this will be a simplified block diagram of OFDM as well as SCFDM. So this red color is nothing but SCFDMA plus black. Normal red color is nothing but OFDMA. So black and red will be SCFDMA. Only red will be OFDMA. So input thing is given input. Then we are going for endpoint DFT. There we are going for IFFT, inverse fast Fourier transformation. Here we are going for discrete Fourier transformation. Then subcarrier mapping. Here we are going to map carrier by subcarrier mapping. All carrier will be undergone by subcarrier and will be mapped, and then it will go for one more algorithm IFFT, which have been used in OFDM, that is nothing but inverse fast Fourier transformation. Then we are going to add cyclic repeat. Then with the help of an analog to digital converter, we are going for transfer. In the receiver side, we are going to remove IFFT will be FFT in receiver side. Subcarrier mapping will be subcarrier D mapping, that is parallel to serial converter, serial to parallel converter. That was subcarrier mapping as well as subcarrier D mapping. Next, what is meant by EQ means, that is subcarrier equalization. With the help of a subcarrier equalization, we are going for inverse discrete Fourier transformation, and then we will be getting the output. So this was the simplified block diagram of OFDM as well as SCFDM. SCFDM may add the concept in transmitter DFT, discrete Fourier transformation. That's all. Other than everything what we have discussed in OFDM, it will be carried out. In receiver side, here we are going to add two changes. One is nothing but subcarrier equalization. Then DFFT will be converted into IDFT. That was the technology.